On September 26, 2022, NASA deliberately destroyed a spacecraft. They aimed it at an asteroid moving through the solar system and drove it in at over 22,000 kilometers per hour. The moment of impact was so violent that it created a debris tail thousands of kilometers long, visible from Earth for months afterward. For the first time in history, humanity deliberately changed the orbit of an asteroid. But here's what makes this more than a scientific achievement. The asteroid NASA practice-deflected is not the one we actually need to worry about. The one we need to worry about is 340 meters wide, and in April 2029, less than 3 years from now, it will pass closer to Earth than most of our communication satellites. DART was humanity's rehearsal. What comes next is the real thing. To understand why the DART mission matters, you need to go back approximately 66 million years. A space rock, roughly 12 kilometers across, struck the shallow coastal waters of what is now the Yucatan Peninsula in Mexico. Within a geological instant, 3/4 of all species on Earth disappeared. The dinosaurs, after ruling this planet for 165 million years, were gone. The Chicxulub crater that impact left behind is still buried under the Yucatan today, 180 kilometers wide, a permanent scar in the geology of our world. This was not a unique event in the history of our solar system. It was simply the most recent catastrophic one. Astronomers have cataloged over 2,000 near-Earth asteroids classified as potentially hazardous, large enough to cause regional or global devastation if they ever crossed our path. Most of them are on safe trajectories, but asteroids move on calculable, predictable paths, and that is what distinguishes them from every other natural disaster civilization has ever faced. You cannot stop an earthquake. You cannot stop a hurricane. But an asteroid follows orbital mechanics, and if you know it is coming with enough lead time, and if your technology is capable enough, you can actually move it. The question is whether that technology works. Whether it actually works, not in theory, but in practice, against a real space rock in the real solar system. What that means for survival planning. Unlike every extinction-level threat in Earth's history before this one, this is the category we can theoretically solve, if we invest in the tools early enough. Before we get to how NASA tested those tools, you need to understand what is waiting in 2029, because this is the context that makes everything about DART feel urgent rather than merely academic. In April 2029, an asteroid named Apophis will pass closer to Earth than the ring of geosynchronous satellites orbiting at 35,000 kilometers. It will skim past at roughly 31,000 kilometers from our surface, close enough to be visible to the naked eye, drifting across the night sky like a slow, bright star. For most people alive today, it will be the first and only time in their lives that they can step outside, look up, and watch a potentially civilization-altering asteroid move across the sky with their own eyes. Apophis is approximately 340 meters wide. That is large enough, on impact, to obliterate a country the size of France. Not an extinction event, but a civilization-altering one, potentially killing hundreds of millions of people depending on where it struck. Apophis is not going to hit Earth in 2029. Astronomers are confident of that. In the geometry of orbital mechanics, there exists a concept called a gravitational keyhole, a region of space so small it can measure just a few hundred meters across. But if an asteroid passes through it during a close flyby, the Earth's own gravity will bend the asteroid's path in precisely the way needed to produce a direct impact on a future return. For Apophis, such a keyhole exists. Whether the 2029 flyby threads that keyhole or misses it entirely depends on measurements that only become fully precise as the date approaches. The difference between a harmless pass and a future catastrophe can be a matter of hundreds of meters of initial position. So when NASA designed a mission to test whether humanity could actually deflect an asteroid, Apophis was always the context sitting in the background. DART was not aimed at Apophis, but everything DART was going to learn would go directly into calculating whether something like Apophis could ever be moved if it needed to be. Now here was the engineering problem that NASA had to solve before they could even choose a target. If you crash a spacecraft into an asteroid 11 million kilometers from Earth, how do you actually verify that you moved it? The velocity change from a single spacecraft impact is going to be almost undetectable, something like 0.5 millimeter per second of orbital speed change. How do you confirm something that subtle without sending another spacecraft all the way back to check? The answer was a binary asteroid system. A larger body called Dimorphos, roughly 780 meters across, orbited by a small moonlet called Dimorphos, which measured about 150 meters in diameter, approximately the same size as the Great Pyramid of Giza. When two objects orbit each other, their orbital period, the time it takes the smaller body to complete one full loop, can be measured with extraordinary precision from Earth, simply by tracking the tiny fluctuations in brightness as Dimorphos passes in front of and behind Dimorphos. Before impact, that orbital period had been measured precisely at 11 hours and 55 minutes. If DART's impact changed that orbit, telescopes across the entire planet could confirm it independently, without any additional spacecraft. The target selection was itself an act of engineering intelligence. Build the verification system into the natural geometry of the asteroid, and use the whole Earth as your measurement instrument. Most spacecraft are built to survive. The Parker Solar Probe was engineered to function inside the atmosphere of a star. The Voyager probes were built to outlast decades of deep space travel, until they crossed out of the solar system entirely. DART was designed to do the exact opposite. DART was built to be destroyed as completely and effectively as possible. And the engineering decisions that define it are fascinating precisely because of that inversion. The spacecraft weighed about 570 kilograms at launch, roughly the weight of a grand piano. It carried a single primary instrument, a camera called Draco, which served simultaneously as the mission's eyes and its navigation brain. In the final 4 hours of approach, DART was operating with complete autonomy. At that distance from Earth, a radio signal takes 38 seconds each way. At 22,000 kilometers per hour, waiting for a human command and its confirmation would mean the spacecraft had traveled thousands of kilometers during the exchange. There was no possibility of real-time human control. An onboard system called SmartNav was reading the images from Draco, identifying Dimorphos against the background of space, calculating the exact center of the asteroid, and adjusting the spacecraft's trajectory entirely on its own, continuously, silently, right up until the final second. And then came the approach. Every second, Dimorphos grew larger in Draco's frame. The craters became visible. Individual boulders on the surface became distinct shapes. The irregular, ancient form of an asteroid that had drifted through the solar system for billions of years filled more and more of the image. Every second, the asteroid doubled in size in the frame. The final image was transmitted when DART was roughly 12 kilometers from the surface, 2 seconds before impact. It shows the terrain of Dimorphos in stark detail. Boulders, shadows, the raw, undisturbed surface of a world that had never been touched by anything from Earth. Then the transmission cut. The next signal humanity received from that location was silence. The orbital period change was the headline result, but when the full analysis arrived in the months following impact, researchers found something that nobody had fully anticipated going in. DART did not just nudge Dimorphos' orbit, it changed the asteroid's shape. Before the impact, Dimorphos had a rounded, roughly symmetrical form. Post-impact observations showed the shape had been measurably and permanently altered. Mass was lost, the surface was restructured, and the object itself was reshaped by the violence of the collision and the loss of excavated material. The asteroid that ESA's Hera spacecraft is now traveling to examine is a physically different object than the one DART approached. Scientists had expected to move a world. They did not expect to reshape one. And that distinction matters enormously for planetary defense, because it confirms that the kinetic impactor technique delivers more force than the conservative models assumed, while also making clear that understanding a target asteroid's internal composition before deflection is critical, because the same impact energy produces very different results depending on what the asteroid is actually made of and how loosely its material is bound together. Humanity's first experiment in asteroid deflection did not just answer the question it was designed to answer. It opened a deeper set of questions that only the next mission can resolve. DART answered the question humanity had been asking for decades. Can we move an asteroid? The answer is yes. Hera is here to answer the much harder question that DART's results made necessary. How much can we move one? And why? Hera launched in October 2024 and flew past Mars in March 2025, using the planet's gravity to adjust its trajectory toward the Dimorphos system. It is currently en cruise through the asteroid belt and is scheduled to arrive at Dimorphos in late 2026. When it gets there, it will spend months conducting the detailed survey that DART's design never allowed, measuring the precise mass of Dimorphos, mapping the impact site, and using radar instruments to peer beneath the surface and characterize the asteroid's internal structure. Without knowing the mass, you cannot calculate the exact efficiency of the deflection. Without understanding the internal structure, you cannot build a reliable model that extends to other asteroids. Right now, humanity's deflection formula has exactly one data point. Hera's mission is to fill in every variable that DART's impact left undefined. That formula is not abstract. It is directly relevant to Apophis. When NASA's OSIRIS-APEX spacecraft arrives at Apophis during its 2029 flyby to study it up close, it will be characterizing that asteroid against exactly the framework that DART and Hera together are building. If Apophis ever needed to be moved, the decision about how to do it would run through the database this chain of missions is assembling right now. On September 26, 2022, a 570-kilogram spacecraft drove itself into a space rock at 22,000 kilometers per hour and changed the orbit of that space rock by 33 minutes, more than 3 times what anyone had officially predicted. For 66 million years, since the last great impact rewrote the history of life on this planet, no species that ever lived here had any answer to this particular problem. They could not see it coming. They could not measure it. They certainly could not move it. We can. For the first time in Earth's history, survival may no longer depend on luck. It may depend on whether we choose to use what we have already learned. Because on September 26, 2022, humanity answered a question no civilization had ever answered before. Yes, we can move an asteroid. If this video was worth your time, the like button genuinely helps the algorithm show it to more people. Subscribe for the next entry, because we are going deep on Apophis, the gravitational keyhole that could determine the fate of hundreds of millions of people, why the 2029 flyby is only the beginning of the threat window, and what NASA is doing right now to make sure that keyhole is never a question again.